Bismillahirrahmanirrahim. This is Pakistan Generation Food Type and class first year grade 11, chapter number 3, and we already started the modern theories of covalent bonding, and we are talking about valence bond theory. And the last lecture we done the sp3 hybridization with the example of methane. But there are 3 examples. For the valence bond theory, there are 3 hybridizations: sp3, sp2 and sp. In the previous lecture, I told you about sp3 hybridization with examples of methane. Now today, we discuss the hybridization, sp3 hybridization in ammonia. sp3 hybridization in ammonia. So, you done the definition of sp3 hybridization when one s atomic orbital intermixes with 3 p orbitals which have the different energies to form equivalent 4 sp3 hybridized atomic orbitals having same energies and shape are called hybridized atomic orbitals, and we done for the methane. Now ammonia. Dear students, in ammonia, nitrogen is the central atom. This is a nitrogen with the atomic number 7, and electronic configuration is 1s 2s 2, then 2px1, 2py1, 2pz1. 7. 2 plus 2, 4 and 3, 7. There are 7 electrons. So you are seeing that 3 unpaired electron for the L shell, and S is complete with the 2 electrons. I will write here the ammonia, and you are seeing that ammonia is bonded with 3 hydrogens, and there is one lone pair. 3 hydrogens, 1, 1, 1, and there is a one lone pair filled, not participating. So students, mind it, there is no need for the excitation as we done for the carbon. In the carbon, there was excitation state. There is no oxidation. In the excitation state, this is a ground. This one is called ground state, and there is no excitation, direct hybridization. 1s2 is complete. And now they are going to intermix S1 and P3. So they are going to be intermixed with each other. And in the previous lecture, I wrote the shape, how they are intermixing, and I told you this is not given in your book, you must write. So they are going to be adding 2S2 plus 2px1 plus 2py1 plus 2pz1 plus. This is this one is a hybridization state. This is a hybridization state. It means that you have 4 equivalent sp3 hybridized atomic orbitals. 4 equivalent sp3 hybridized atomic orbitals. These are 4 sp3. Also for the formula of methane CH4, there was also sp3 hybridization, now also sp3 hybridization. But the difference with the methane and ammonia is, one is a complete filled lone pair, not participating, and 3 are going to participate. They are all equivalent, all are sp3. 3 are participating and 1 is not participating. If you see the structure of ammonia, 1 is a filled and 3 is not filled. So if I am going to draw the structure of ammonia, you can find here. This is the nitrogen, and this nitrogen is surrounded with the 4 sp3 hybridized atomic orbitals with the tetrahedral corners, 4 like this one. Out of 4 sp3 hybridized atomic orbital, so you can see 1 is partially filled, and this one is going to overlap with 1s1 of the hydrogen. This is going to fill with 1s1 for the hydrogen. This is going to be filled with 1s1 for the hydrogen. Like this. 3 sp3 hybridized atomic orbitals form sigma bond with hydrogen, and 1 is going to be as a lone pair. And you know the Westphal theory, the lone pair occupies more space than bond pairs, and it creates repulsion between lone pair and bond pair, and this is a function of the lone pair. And the geometry is deviate, change from tetrahedral to trigonal pyramid. Irregular geometry, trigonal pyramid. Trigonal pyramid, and angle is 107.5 degree. So the question may be asked that in sp3 hybridization, methane form tetrahedral geometry, ammonia also sp3 hybridization, geometry is trigonal pyramid with the angle 107.5. reason. This is the reason. In methane, there is no lone pair. In methane, there is no lone pair. All are the bond pairs and give the regular tetrahedral geometry with 109.5 angle. But in the case of ammonia, there are 2 electrons which are not participating, lone pair, non-bonding electrons, and function I told you, van der Waals repulsion, they create repulsion bond pairs and lone pairs, so they deviate the angle, decreases the angle and change the shape of the ammonia. this is again sp3 hybridization, and the structure of ammonia. Write down this. Hurry up, students. Write down this. Again, third example of sp3 hybridization. sp3 hybridization, the structure is now water. Water also gives sp3 hybridization. So central atom is oxygen. Atomic number is 8. Oxygen atomic number is 8. So students, there is a 1s, 1s2, 2s2, 2px1, and there are 8, 2py1 and 2pz1, 2 and 2, 4, 5, 6, 7, like this. So we are talking about sp3 hybridization, means this is a ground state. Means mixing of 2s plus 2px, 2py and 2pz. The difference is here with methane and ammonia. This is the paired lone pair. Two hydrogen there are. Again, there is a no need of excitation. No need of excitation. So 2s2 plus 2px2 plus 2py1 plus 2pz. They all form 4, 1, 2, 3, 4, S1p3. So 4sp3 hybridization. Again 4sp3 hybridization, but the difference is this is the 1sp3, 2 electrons. Again sp3, 2 electrons, sp3, 1 electron, and sp3, 1 electron. Yes. So 2 are paired and 2 are unpaired. They are as lone pair. These are the 2 lone pairs. So this is the hybridized state. Hybridized state. So structure: oxygen is surrounding with 2 lone pairs. These are sp3 hybridized atomic orbitals and acting as lone pairs. There are lone pairs. And there is a third sp3 which is partially filled like this. So if you see this one, these two lone pairs, maximum repulsion. Between lone pair and lone pair, they have a maximum repulsion. And repulsion between lone pair and bond pair, and also bond pair and bond pair. So it means that there is a angular shape. So like this one. Oxygen. Like this. These two lone pairs have a great repulsion between them and occupy more space, not only here but repulsion between bond pair and lone pair and lone pair and bond pair and bond pair and bond pair. So geometry will be angular, V shape. Angle is further decreases 104.5 degree. 104.5 degree angle. So students, this is the structure of water. Structure of water according to hybridization approach. According to hybridization approach, we finish the sp3 hybridization. Three examples I explained: methane, ammonia and water. Must read the book very carefully and watch my lectures also very carefully. Write down in your copies and practice and see the exercises, questions. So this hybridization, sp3 hybridization is over. Now we start another hybridization approach, and this is called sp2 hybridization. Now sp2 hybridization. In sp2 hybridization, the definition is intermixing of one s atomic orbital with two p atomic orbitals having different energies. After intermixing, results give equivalent same 3sp2 hybridized atomic orbital, 3sp2 hybridized atomic orbitals having same energy and shape are called sp2 hybridized atomic orbitals. So shapes are given in the book. There is one S, the S, and 2P means PX coordinates and PY. They are going to intermix. They intermix with each other. S1 and B2 give 3 sp2 3 as the shape of sp2. Same I told you. The shapes of the all hybridized atomic orbitals sp3, sp2 and sp are same. This is the shape of sp2 and there are 3, not 4. 1s and p2, they intermix with each other. If you see the shapes are here. So there are 3 sp2. 3. 1, 2, 3. sp2, sp2 and sp2. And I told you in the previous lecture, for the sake of simplicity, we don't write the symbol low. No need for writing this. 1, 2, 3, yes, there are 3 sp2. So this is the definition and example I am telling you. There are 2 examples given in your book: boron trifluoride and ethene. Sigma bond, sigma bond, sigma bond, pi bond, sigma bond, sigma bond. 1, 2, 3, 4, 5. 5 sigma bonds and 1 pi bond. 5 sigma bonds and 1 pi bond is going to be formed. Ethene. And boron trifluoride give sp2 hybridization approach. Now, students, when we are going to talking about the sp2 hybridization, and I told you the examples of boron trifluoride. So, boron atomic number is 5. 1s2, 1s2. And 2s2. 2px1, 2p0y, 2pz also. There are only 5. There are only 5. 1s, 2s, 2px, 2py, and 2pz. So there is only one unpaired. There is only one unpaired. That's why it can form only one bond. So ground state is not the. It's a ground state. So, but boron shows 3 valence. Valence number of boron is 3. So that is why the excitation state is going to be one s2, 2s1, 2px. And it is going to be promoted in the 2py, 2pz0. So you have 3. See this unpaired. This is the excited. This is the excited state. So that's why boron 5, 1s and 2p, according to this, 1s and 2p, this is the 1s and 2p, they are going to intermix. So, s1 plus 2px1 plus 2py1, they are intermixing with ratio 1 and 2 ratio. 1 and 2 ratio. So give 3sp2. sp2 hybridization. So there are 3 sp2 hybridized atomic orbitals. So this is a boron, 1 sp2, second sp2, and third sp2. There are 3 sp2 hybridized atomic orbitals, and fluorine has a 1 in the 2pz. If you write the electronic configuration of fluorine, there is a 1 electron in 2pz, atomic number 9. That is unpaired. 2pz is unpaired. That is why must write this one. This is the 2pz of fluorine. 2pz, 1 for the fluorine. This is a sigma bond. And also shape of P is like this one. This is also 2pz1 for the fluorine, sigma bond. And same. This is a 2pz1 sigma bond. Physical, yes, trivalent. According to hybridization approach, the boron has a trivalent, 3 valency after transferring from 2s to 2py, and after the hybridization intermixing 3. So that's why boron, trifluoride, you done the Vesper theory. The angle is 120. Angle will be 120, and it shows triangular planar. It shows triangular planar, 120 angle, and you done in the Vesper theory. So, dear students, this is the sp2 hybridization when 1s and 2p mean px and py mixing to give the equivalent 3 sp2 hybridized atomic orbitals, and the shape of hybridized big lobe and small lobe, there are 3. So this is the electronic configuration, 1s2, 2s2, 2px1 only 1 electron unpaired, so it does not form 3 bonds. 2 are empty, so excited state. Now this electron is transferred to 2py. There are 3 unpaired electrons here, and they are going to intermix in the hybridization process, intermixing 2s1 plus 2px1 plus 2py1, and they are going to give a 3 sp2 hybridized atomic orbital, and this is the boron, and 1, 2, 3 sp2 with the 3 corners. And I told you 3 fluorine atoms are involved in here, and the electronic configuration of fluorine, if you do atomic number 9, there is a 1 electron in 2pz, which is unpaired and overlapping straight to form a sigma bond with the boron. Likewise, all the 3 bonds are going to be formed. When these 3 bonds are going to be formed, so the angle is 120 degree as we done in the Vesper theory, and also the regular triangular planar structure is going to be formed, and there is no lone pair. There is a no lone pair, so that is why boron trifluoride gives triangular planar structure with the 120 angles. See the structures given in the book, and this 3sp2 means S and P. So there is a 33.33% S character and 66.66% P character. and ratio is a 1:2 ratio. As we go, I told you last time that S percentage is going to be increased and P percentage is going to be decreased. In the SP3, 2575. Now in the SP2, 36.66. The S is going to be increased and P is going to be decreased. So this electronic configuration is given, and thus angle 1 SP2 120, 3 SP2 hybridized orbiters, and each partially filled. The partially filled 2p orbiters, 3 fluorine, I told you 2pz, they are going to be formed. And must draw this. Must draw this one. This is not given in your book. That's why sp2 and p orbiters, they are going to be formed 3 bonds to give 3 sigma bonds. So inshallah in the next lecture, so we will discuss an example of sp2 hybridization next lecture. So this is the ethene. So next inshallah we will discuss about ethene. Thank you very much.